Good day.
Okay. So hello everyone. I don't see many of you still, but I hope everyone is arriving. So the last time we talked about matrix equations, and then we talked about permutations. So I hope it's time to start the reason why we needed permutations, that is to discuss determinants. So let me start from slightly far, from a bit of motivational pieces. So, so I hope everyone sees the whiteboard, and I've shared a link in the chat for those who need it. So everything is fine?
Yes.
Okay, at least someone sees everything, so that's good. So consider the following system of two linear equations with two variables. We already discussed elimination method, Gauss method on one hand, and well, so for any particular numbers, we are able to solve the system. If A, B, C, D, E, F are some particular numbers, we can easily solve it. But, well, some smart ancient people one day arrived to the following thought, that maybe we can solve the system in general for any letters A, B, C, D, E, F. And then we will produce some formulas, x equals something, y equals something. So those formulas will depend on the parameters A, B, C, D, E, F. This way we obtain kind of a solution where for any particular A, B, C, D, E, F, we have to put inside those values and we obtain the result. A pre-cooked formula, a ready-to-use formula, a ready-to-use solution. That's a very logical thought. Very often we do things like that. For example, when you study square equations, quadratic equations in school, you kind of first discuss, I hope, how any particular equation can be solved by separating the square, by extracting the square. And then you discuss that from this, we can find the formula for the roots. And after you found the formula, you may forget about the logic and simply use the formula straightforward. So let's follow their way for a moment. So to follow, let me suppose that A doesn't equal 0. There are two cases, A equals 0 and A doesn't equal 0, but A doesn't equal 0 is a more general case. It consists of many more cases, right? There's almost any number, only 0 doesn't satisfy this. So I will today omit the case A equals 0, though it may be also discussed. Then I'm able to write the matrix, and I'm able to divide the first line by A. So I obtain this. Then after I obtain this, I may subtract this line from this with coefficient C, so that this C vanishes. Then what I obtain is as follows. The first row doesn't change, and here I obtain D minus B over A times C, right? I take B over A, I multiply it by C, and I subtract the result from D. Similarly, here I obtain F minus E over A times C. No questions yet? Well, to continue, I need to divide the second row by this number. And again, the question arises whether this number is 0 or non-zero. Let me suppose this number is also non-zero. Let me suppose this for a moment. Then I am able to divide, and the result is as follows. I just formally divided. So if I take this number, I can simplify it by multiplying by A both sides. The result looks as follows. AF minus CE divided by AD minus BC. So that's so the second equation reads 0x plus 1y equals well, this expression. So y equals this. This is the general formula for y. It depends on 6 parameters. When you pick some particular values of A, B, C, D, E, F, you can put them into this formula and find y. Similarly, one may find the formula for x. I will not subtract the equations, etc. I will simply write the correct formula immediately. Just give me a second to do this. No. BF minus. Sorry. I have to look at the equations to produce the correct formula. Like this. So again, later we will discuss how I memorize those formulas by heart and how this works. But right now, let me just note that those formulas look similar and their nominator and denominator look similar. Both have something by something minus something by something. Moreover, their denominator is the same. So ancient people didn't stop here. They applied the same method for 3x3 systems. We will skip this. It takes lots of time. 3x3 system is much harder. Still, they were able to obtain the general formulas. And those formulas look like this. X equals some huge expression divided by some huge expression, y equals some huge expression divided by some huge expression, and z equals, well, the same. And the expression in the denominator is the same. We usually denote it delta. Again, we're going to return to this slightly later. So this means that those kinds of expressions that appear in those formulas are interesting. And we're going to see soon that those expressions are determinants. Are there any questions right now about this small story? Okay, then let me quickly, even more quick, discuss a second story, and then we go to, well, studying determinants. So the second story is as follows. Consider a triangle and let one of its vertices, for simplicity, be the origin, the 0, and let another two vertices be x1, y1 and x2, y2. So this is a triangle. And a triangle has its area. So there is a very logical question, how to find this area using those coordinates? There are two ways. Everyone shall know one way from school. That's Heron's formula. There was an ancient Greek mathematician who produced a formula for the area of a triangle using the lengths of its sides. However, this formula is very hard to use. It requires finding 4 values, and each of them includes square roots because of Pythagoras theorem, right? To find the length of each side, I will take some square roots of something. And then you need to multiply everything. And then in the result, you take another square root. This is a hard formula. I claim that this particular problem is much easier. It doesn't require to use this complicated formula. Indeed, one may consider the following. The picture I draw will work only for this case where this vertex is slightly above than this. For another case, you will need to kind of redraw the picture. So we can theoretically consider several cases. So I may consider this triangle. Its area is very easy to compute. Its area is x2 multiplied by y2 divided by 2, right? If the coordinates of this vertex are x2, y2, then I simply take the area of this rectangle and divide it by 2. Likewise, the area of this trapezium is easy to find. The length of this segment is x2 minus x1, and the and those what are they called? I forgot the word. Well, those sides of the trapezium, they are well, y2 and y1 respectively. So this area is y2 plus y1 over half. Yes, the average between those lengths multiplied by this altitude. Okay, this is the area of this trapezium. And if I add them together, I get the area of this figure. So I can take this figure and subtract this area to obtain the area of the triangle. So I obtain this plus this minus this area, that is x1, y1 over 2. I may simplify this, and the result is as follows. It is 1/2 of x1, y2 minus x2, y1, or maybe vice versa. It depends on the order of the vertices, but if I put the sign of the absolute value, then this formula works, because the area needs to be positive. Questions?
Well, so we try to find the area of the triangle, and we have so that 2 ways. The first one is not the most suitable because of a lot of squares, while the second, the second one is much more convenient, and we do it via finding the areas of the 2 figures. No?
Yeah, we did it through finding areas of 3 figures, adding 2 of them and subtracting the third one. But the result is a formula that we can now use. We don't need to remember the way we constructed it. This formula now can be memorized and used to find area of any triangle.
Okay, thank you.
Okay, and so what is interesting is that this formula looks similar to the formula from the previous problem. Those two formulas look similar, something by something minus something by something. Well, on one hand, that's because they are very simple. Well, there are not many ways one may combine 4 variables into something simple. So maybe that's a coincidence. But if you study parallelohedrons in 3-dimensional space, or maybe not parallelohedrons, but first, if you study, say, tetrahedrons, okay? If you consider a tetrahedron in 3-dimensional space and consider its volume, the same problem like this one, but in 3-dimensional space, then you will arrive also to some expression like this. And the magic is that this expression will be the same as the expression in the formulas for x, y, z in this problem. So we will discuss the formulas for this the next time, as far as I remember the course. And the areas we will discuss somewhere in the end of the course, unfortunately, but we will return to this topic later, and we will see why the result is indeed the same expression. And right now, let us talk about this expression, which is, well, the determinant of a matrix. So by definition, determinant of a square matrix is some very hard to understand sum. Many people have problems with it. It is a sum over all possible permutations of n elements of the following products. Sorry. So for each permutation, I take some element in the first row, some element in the second row, some element in the third row, etc., and multiply them together. And then I add all such results, but not like this. There is a mistake in this formula. Do you see it? Okay. Let me try to apply this wrong formula to the 2x2 case, and we will see what is the mistake in a moment.
Should F be maybe instead of F there should be N?
No.
No?
No.
Okay.
F is an arbitrary permutation from Sn. So again, let me try to apply it to the case 2x2. In 2x2 case, so I need all possible permutations. There are two permutations, right? 2 factorial is 2. This and this. So for the first one, I write the following formula. A1 and then f of 1. F of 1 is 1. A2, 2. I simply read the columns. For the second one, I write A1, 2 and A2, 1, again, by reading the columns. And if this formula were correct, I would write plus. However, we just discussed that our motivation looks like this. This expression, well, it obviously makes sense. I'm sorry, there is some problem with my board. Aha, connection restored. So, in fact, to make a useful expression, we need to put a minus here. And in this definition, there is a sign here. That is -1 to the power of f, which is synonym to sine of f. We discussed it last time. For each permutation, we compute its sign. So some of them are even permutations and some of them are odd permutations. And we put this sign before this monomial. Then the result is called the determinant. This definition might look very, very strange, but again, it's not like we just randomly decided, let's consider this expression. No, it was like looked, how to say, it was spied on from the nature. It exists in the nature like the area of a triangle exists. We simply looked which expression comes from this area. And so we made a corresponding definition. But again, the proof that they are the same expressions will be later. So that is the determinant. Unfortunately, this definition is very hard to use. If I have some particular determinant, some particular values, I can, for the 2x2 case, I can easily apply the definition, multiply this by this, minus this by this. That's easy. However, if I consider a 3x3 case, give me a second to find some example. If I consider the 3 by 3 case, now I need to consider 6 possible permutations. That's much more than 2. So here I have written down all 6 possible permutations. Also, I need to find which of them are even, like this one, and which of them are odd. So this one is odd because it contains a transposition 2 and 1 are exchanged, and nothing else is, so it has one inversion. This, so the next I will simply write for all of them whether they're even or odd. So you are free to check that this is correct. In fact, I recommend to check at some point, but maybe not right now. So then for each, I may write the corresponding product. For example, for this one, I take the first element, that is 2, times element 2 with indexes 2, 2, that is this 3 in the middle, times the last element with indices 3, 3, that's this element. So I go through this diagonal. Then minus, let me consider this one. In the first row, I take the second element, that's 1. In the second row, I take the first element, that's 5. In the third row, I took the third element, that's 3. So this triangle, etc. For this one, I find 1 times 2, 3, that's this. 2 times 3, 1, that's this, 1. For this one, I find 2 times 2, 3 means this element 2, times 3, 2 means this element 4. For this one, it is 3, 2, 1 is 5, and 3, 2 is 4. And for the last one, 3, 3, and 1 from here. And that's it. Okay?
So we should in that formula to put some sign, like sign before this.
Yes. So the sign is the sign of the permutation. We discussed it last time.
Yes, I mean that the problem with the formula was the sign of
yes, the problem of the formula was that it is not just a sum, but it is a sum with plus minuses, where the sign is defined by this factor I have inserted inside. Now the formula is correct. Minus 1 to the power of f. The same as sine f.
Okay.
So now I can, well, compute this. Let's do it. So that's 3 plus 2, 5, minus 11. Minus 11 minus 9 is minus 20. 60 minus 20 is 40. The result looks fine. So this method works. But if I have a determinant of size 4 by 4, I will need 24 summons. And if it is 5 by 5, I'll require 120. That's too much. I can't deal with this with pen and paper. And the computer can. However, for the computer, let me ask about 1000 times 1000 determinant. 1000 factorial is a huge number. The computer will also have problems. So this method, while it works as a definition, it is very impractical. We need to have some more convenient, some better way. And such a way exists. It is called Gaussian method, elimination method. Our course comes to the elimination method again and again. It is, repetitive. We will see that many different problems will be solved by the same method. Well, that is life. So this problem may be solved by elimination method. That's because when you apply the first type of transformation, elementary transformation, when you add one row to another with some coefficient, the value of the determinant doesn't change. The matrix becomes different, but the determinant of this matrix is equal to the determinant of the previous one. Like this. This wonderful, well, how to say? This wonderful
Maybe expression.
Сейчас проблема со связью.
Да, связь
Давайте.
прервалась.
Hello.
Hello, we can hear you.
Something wrong was with the connection.
Aha, you didn't hear me.
Yes.
You stopped on how to call it. Let's call it.
Let's call it what? I don't know what I was talking
Maybe expression.
Yeah.
Special method, another method, which is better.
Wait, that was far long ago. Okay, so I was saying that we can use elimination method because it so happens that for each elementary transformation, for each elementary transformation of the first type, when I apply it, the matrix becomes different, but the determinant stays the same. So this gives us the idea that maybe we can use many elementary transformations and make the matrix simpler and find the determinant for a simple matrix, not for a hard one. That's the basic idea. And so, well, let's try. Let me take the same matrix as in that example. And let me try to apply some elementary transformations to make it simpler. Well, the first move might be to exchange those rows, right? To apply the transformation T13 to exchange those rows. Well, the problem is that I know that operations of type L don't change the determinant, but what about T? Who remembers the lectures?
It means to transpose, like to change.
No, not to transpose, to change two rows.
Yes, I mean this. So transpose doesn't mean the same as change the rows, yes?
No.
Okay.
Transpose is
sorry.
When
sorry.
What is the question?
I just can mix up them. I mean, change the rows, sorry.
Yes, but that's not the question. The question is, if I change the rows, so if I write it like this, what becomes with the determinant? Does it change?
It's still the same.
No,
Oh.
it is not. It changes slightly, but how? It was in the last lecture. Well, it should have been. I didn't recheck the lecture notes. But I think the other group remembered it, so should you?
Maybe it changed the sign?
Yes, it so happens that if I apply any transformation T, if I exchange any two rows, then it changes the sign. That's very strange, but that's how it works. So we need to be careful. We need to remember this fact. Whenever you apply this transformation, you need to not forget to change the sign. Now, I may use L-type transformations. So I may subtract this row from the next row with coefficient 5. 3 minus 5 times 4 is minus 17. 2 minus 3 times 5 is minus 13. Similarly, if I apply this for the last row, I obtain 0, 1 minus 8 minus 7, 3 minus 6 minus 3. This is the result. Now, let me subtract this row from this row. Then I obtain minus 10 minus 10. And when I see minus 10 minus 10, it makes sense to use the operation D. I can divide this row by 10 or even by minus 10. But the question is, does the determinant change? And if yes, then how? To find out, we may look at the definition. What happens with this formula? Well, okay, yeah. What happens with this formula? If I take, for example, the second row and divide by some number.
Then it's become lesser.
Well, it becomes this times smaller, right? If I divide everything by minus 10, then this, I mean, the entire second row, then this element, the second element in this product becomes divided by minus 10. Then the entire sum becomes divided by minus 10. So the next determinant that I will write is this determinant is the previous determinant divided by minus 10. Then to make them equal, I need to multiply it by minus 10. In other words, in this operation, I'm taking this factor minus 10 outside of the determinant. I've seen a common factor in this row and I take it outside like this. And here 1, 1 remains.
But we take it just from the one row. Why we write it as we multiplicate by an by a whole matrix?
Yes, but I multiply not so this is not a matrix, this is a determinant. The vertical line mean the so there are two notations for the determinant, that of a matrix or simply vertical lines. So this is a number. A number which I haven't found yet, but still this is a number. Yes, that is slightly counterintuitive. We first discuss multiplying matrices by a number, and now we're using some totally different operation. Now we're multiplying only one row by a number, but that's life. We are interested in this operation now. Any more questions? This is the most.
And could you again explain why we get minus in after the first function?
Well, I didn't explain it the first time. I just said look into the lecture notes. So you simply have to memorize that each operation T gives you a minus. But well, I can theoretically explain. The reason is that in this formula, when you swap two rows, then two of those elements will change places. And if two of the elements change places, then the sign of f changes. I'm not sure whether this is very easy to understand, but if it is hard to understand, simply take some time and reread the corresponding part of the lecture notes. It will be there. This part was kind of easier to explain. That's why I tried to explain it. This part is maybe slightly more complicated. Any more questions? Then let me finish the computation. So minus with minus cancels. Now it is plus 10 times some value, which I haven't found yet. And so now I take this row and subtract from the next one. Well, I mean, add it 7 times to cancel this. Then this becomes 7 minus 3, that's 4. And now I claim we can find this by using some theorem from the lecture. No? Was there any person who was on the lecture?
I was on the lecture, but I didn't get the whole ideas.
Okay.
We all were, but
Okay, I see.
we're still thinking.
Okay, that's very bad, because there was a wonderful theorem that you really needed to memorize that says the following. If you have a determinant of a triangular matrix, if all the elements here are zeros, then the determinant equals simply the product of the elements on the diagonal. The reason for this is as follows. So if you apply the definition of the determinant, well, it will have one monomial that is this times this times this. And in all other monomials, like for example, this one of the elements will always be below the diagonal. So it will be 0. Again, I will not formalize this proof. It is possible to do so, but that's lecturer's job. So I will simply say that, well, we can prove that this huge sum of n factorial different summands, all of them will be 0 other than this one. Only this one will give us any information.
Oh, I see. I just really saw this about triangle matrix, but didn't really get what was the other part. So I see. Thank you.
Very good.
In practice.
And so, yes, and so now we have a practical algorithm. You take any, well, determinant, you can do some steps, arrive to a triangular matrix, and then apply this rule. And that's it. We're able to find any determinant. Which is easier? We solved the same determinant by 2 methods. Was this easier or this? It's hard to see. They were more or less equivalent. They both took like half a page, and well, they both required some computations where you can make mistakes. However, in the 4x4 case, this one will become slightly harder, but the first one will become 4 times harder. And in like, I don't know, say 8 times 8 case, it will be impossible for you to do the first way with pen and paper. And the second one, well, will be very frustrating, but possible. It's not our goal to give you 8 times 8 examples, exercises, but still, it is quite possible to do so. And similarly, for the computer, the second way is much better because the first one requires something like n minus 1 times n factorial multiplications. So O of n plus 1 factorial, one may say. And this method requires something like n cubed divided by some number. I don't remember. It is either 3 or 6 multiplications. I always have problems remembering which one. That's because there are some, well, similar computations where you obtain different results, 3 and 6, but doesn't really matter. That's O of n cubed. And again, that's much, much less. This one is exponential. This one is polynomial. This is very much faster. So by this method, you can do 1,000 by 1,000 determinant in fractions of a second on any computer. And if you take more time, you can do bigger ones. If you take more time and better computers. That's the idea. Any more questions at this moment? Then one final thing I want to say is that we're not, final not meaning that we finish here, but I mean about this is that we also may use the operations not only on rows, but on columns. It so happens, and I think it was proved on the lecture or will be proved in the next one, I don't remember the order. It so happens that if you do operations not on rows, but on columns, everything also works. By works, I mean that if you perform an L-type operation, the determinant doesn't change. If it is T, then the sign changes. If it is D, then the factor needs to be extracted outside. So we have some freedom. We can choose whether to use operations on rows or on columns. That's interesting. It will sometimes help us. Okay, we have some tools. Now let's go to practice. And here I have a problem for you. Let me copy. Okay, so please consider this problem. It is a determinant like the previous ones, but it has two small complications. The first is that it contains not only numbers, but also letters, variables. It contains x. Well, that's not very good, but manageable. However, the second problem is that it is of variable size. It has some dots inside. So the 0th question, which is not the part of the real question, but still is important to discuss, what is the size of this determinant? What is the size of this matrix? Hello?
N minus x.
N by n.
Okay, both are wrong.
Mm.
N minus x is, well, x is like a variable, so n minus x is not a number.
So
And-
n, I
And
guess.
n it looks correct, but it's not correct. No, it's not n by n. Look carefully.
Then that will be definitely n minus 1.
No,
Uh,
look carefully. You need to count how many elements does, well, the diagonal have.
I guess it's n plus
N plus 1.
N plus 1 times n plus 1, because it has 1,
Yeah.
2, 3, etc. n, but it also has this. Okay, that's just a stupid trick, but there is always some confusion at this point. So I start with this question so that we are prepared. Okay, now that we have discuss this confusion, let's compute the value of this determinant. What does it equal to? Your ideas? How to do this?
Maybe we will use a triangle method as we discussed before.
Okay, so we want to simplify this
Yeah.
matrix, but how? What kind of action you will suggest? What to
Maybe, maybe, вычесть, я забыл.
Subtract.
Maybe subtract the last row with the first, and by this algorithm go to the center.
Okay, very strange, but well, it will partially work, but there is an easier idea.
Use the Gaussian elimination method.
Yes, but how exactly? Which kind of operation you would advise?
Then we should just get the zeros in the first column.
Mhm.
And that for that, I suggest every row subtract from every next row subtract the first one.
Okay, that is indeed the most straightforward application of Gaussian elimination. And in this particular problem, it works very well. It is similar to the idea Alexander announced, but it is in fact kind of easier here. Because the first row doesn't contain x, so it's more easy to subtract it from everything. The second row becomes 0 minus x, 0, etc., 0. The next row becomes 0, 0, 1 minus x, etc., 0. The last row is many zeros, and the last one is n minus 1 minus x. Well, we're lucky. This matrix is triangular. Okay, I'm sorry, my triangles are kind of weird shape, but still. So the result can be obtained by simply multiplying the elements on the diagonal, and that's it. This is an interesting answer. You might see that if x is some integer number, then this looks similar to a formula for, how to say, I always forget the word, for this. How is it called? You didn't have them in discrete mathematics, right? But you had them on calculus. How are those things called?
Permutation?
No.
Not permutation.
No.
It's something.
Combination?
It's
Number of
something.
This is
we know-
factory. This is
Okay, I see.
this is this is binomial coefficients.
Binomial coefficients. Okay. Yeah, that's one synonym. I wanted another one, but okay, binomial coefficients is good. Thank you. So if x is integer, then this expression is a binomial coefficient with some minuses inside. And if x is not integer, then it is kind of, well, similar expression. But we will not delve into combinatorics today. So, sorry. So,
But what about answer? Don't we need to write a sum of x's and so on? Or it's just fine to...
no, this one looks fine. It is easy
Okay.
to see that there is no way to make it much easier. So
Okay.
why would we do anything with it? The only thing that I might do is take minuses outside, because the answer becomes slightly more pretty. I can write -1 to the power of n times x minus 1 times etc. times x minus n plus 1. Yeah. But even the previous one is okay. So, okay. A second problem of a similar type.
Should we use these similar methods?
Unfortunately, yes. Unfortunately, this problem looks very much interesting, but it gets solved immediately by applying the same procedure. If I add the first row to everything, then this part kind of cancels. Here I obtain 2, here I obtain 6, 8, etc. to n. Here I obtain 0, 0, 3. Yeah?
Okay, but there will be some difference if we to each row add the first one. I mean,
Yeah, I'm doing this.
okay, then that's thank you.
So I added the first row to each row, and the result goes as follows. The left-hand side with minuses cancels. The diagonal with zeros becomes 1, 2, 3, etc. n, and the things above the diagonal become twice themselves. But they don't matter, because the result is simply the product on the diagonal. And thus, it is n factorial. Any questions here? So now let me have a problem that is not so easy.
Maybe we have 0, 2, 6, 8 in the previous, but I just cannot get. So do we have
Okay.
now more columns, or just how we get the 6
Yeah,
elements in the
I've written
second?
the next column. I've written here the fourth column. Again, these dots mean there are many columns in between.
Yeah, I understand, but it just was.
Yeah, I just wanted to write this column so that you see that after 3, it goes not 4, but 8. To emphasize this, I added one more column.
Okay, thank.
So let me consider one more problem of this type. So this is once again an O. It doesn't have dots here for some reason. That's my mistake. But still, this is an n times n matrix where on the diagonal I have 3 and everywhere else I have 2.
Can we then no, not transpose, but change the rows?
We can change the order of the rows, but will it help? They all look like the same.
I'm thinking about changing the columns then.
But they all look the same.
Why? Then we'll get the zeros in the first column if we replace.
By changing order, it's very hard to change the order and somehow obtain zeros. That doesn't usually happen. Yes.
No, I mean that we need the zeros for the first column, but this the first column can become the last one. So
Okay,
no,
I'm
no,
not
no,
sure.
no.
Yeah,
it's
please.
difficult
Think
to-
this. Raman
okay.
wants to say something else also.
Okay,
I wanted to.
that won't work. That.
Yeah. Raman? What?
Sorry, I wanted to suppose maybe we should subtract the rows from the last one, because in the last one we have 1, the last column, so maybe we should subtract from the previous.
I also don't understand what you're saying. Can you maybe rephrase?
Suggest to subtract each row above the last one, and from each of these rows to subtract the last one. So, for example, we get the fourth row, and then
Like this?
yes.
Okay, that's possible. In fact, it doesn't really matter which row you subtract. You take any row and subtract from all the others. It doesn't really matter which. You will still get the results, but let us take the last one. Then what happens? The bad news is that the last row survives. It can't be subtracted from itself. That's illegal.
I guess there's no other way than just do the other thing, but for the first row, just subtract. Then the first.
Yeah, but nothing will change. It will be also bad.
Yeah. But maybe we should multiply these rows by the some determined, not determined, but by some, like, no, this is our operation elementary. We can not only just sum by 1 or -1, we can multiply it.
Yes, but how will it help? To cancel 2's with 2's, it's logical to, well, subtract without any factor. No, this step looks very, very logical. It is good. The good part is that we obtained lots of zeros. That's wonderful. The only part that is bad is that the problem didn't solve itself in one step. Well, not every problem solves in one step. Yes?
Why can't we subtract the, like, from the last row, first and second, and so on?
Here?
Yes, like
Indeed.
using the main diagonal to reduce.
Indeed. Now I may continue. So I first use the last row on the previous ones. Now I can use the previous ones on the last row. To use those 1, 1, 1, 1 to cancel those 2, 2, 2, 2. Then the result is as follows. I can obtain 0 in every element here by subtracting twice. I subtract this twice and this twice and this twice, etc. And in the last cell, I subtract n-1 times twice the element -1, this element. When I subtract the first row, 3, from 3, I subtract -2. The next time, 1 another -2, etc., etc. So the result, in the result, here I obtain 2n, right? 2n. This becomes minus with minus becomes plus, and here I have -2, here I have +3, so 2n plus 1. Now, how to find this determinant? What is our next step?
It's just 2n plus 1.
It is simply 2n plus 1 because this one is diagonal. So in the previous two problems, we did it with one step. In this problem, we needed 2 steps, but still after them, we made the matrix diagonal. And now we can reap the benefits, multiply the elements on the main diagonal. Questions? Okay, so do we have 20 minutes, right?
Yes.
Yeah.
Okay. Okay, I'm not sure if we have time for 2 more problems that I need, but at least, well, let's start with one and see. So here is a problem, unfortunately in Russian, but I hope everyone can read Russian. So there is a determinant and someone subtracted its rows each from the next one, from the previous one, as follows. So there was some matrix A and someone formed the following matrix B. In the first row, he considered A1 minus A2. From the first row, he subtracted the second row. In the second row, he subtracted the third row. In the third row, he subtracted the fourth row, and so on. In the last row, he subtracted the first row. So the question is to find the determinant of B, to express it through the determinant of A. It's hard to find something, well, like when it has variables inside, but the question is, how is it related to the determinant of A? Any ideas? Well, the first logical idea should be maybe it is equal to the determinant of A. Because we made, I'm sorry, give me a second, because we made many elementary operations, right? So it shouldn't change. Where is the problem with this logic?
But what does this element? But we have the last row, which is also subtracted. And that is why maybe there should be another sign.
Well, that's guessing. Maybe there should be another sign. Why? We performed many L operations. Each operation is the operation of L type, the good one.
But we then, from the last one, subtract the first one. So we get another sign. No.
Maybe when we have to make some easy example.
But we will need to get this identity matrix. No,
I'm sorry, I have no idea why, yes, how identity matrix is connected to this. And I can get the idea of Alexander too. You advise us to try on some example. Well,
yes.
Interesting idea. You are the first one who advised this in 4 years, but why not? Mathematics is experimenting. So let us try to take some particular matrix and look what happens. Well, that's interesting. Let's take this one. Its determinant is -2, 4 minus 6. Now, now the determinant of B is, so from the first row, I subtract the second. It is -2 minus 2. And from the second row, I subtract the first. That's +2 plus 2. Then the determinant is -4 minus -4, that's 0. So we see that it changed, but why? I performed legal operations, subtracting one row from another. Why it changed? Is there some mistake maybe in the theorem that it doesn't change?
No, I guess there's a problem that in this last row, because the last row we subtract the first one, and then just we get another sign of it. Then the
so
others.
0 has the other sign than -2?
No, I mean that the last row changes the sign, has the other sign then.
But even if it had this sign, it would be still 0, which is not the same as the original. No, the sign doesn't have anything with it.
Okay.
We need to look into the logic. Something illegal happened, but what?
I mean, maybe the order, because we have an subtract A first, and the A first is changed before.
Yes, it is changed before. We make simultaneously operations. When we very first time studied elementary operations, I told you that they are done one after another. Then after 1 or 2 problems, I said, but for convenience, we sometimes do them simultaneously, but only when we are sure that they don't interact with each other. And here is the situation when they interact with each other. The first row from the first row, we subtract the second row, and from the second, we subtract the first. Of course, those two operations can't be done simultaneously. They conflict. That's the reason why this is an illegal move. But by illegal, I mean that there is no proof that it doesn't change the determinant. Well, and in fact, it sometimes at least does. We have an example. But now we come to the problem. What is the result? So, okay, the determinant changes, but how? How to find the result?
Well, we just guessed the first subtract the last row from the others. And then we just change the last row, yes? We have this order.
One can say, yes, that we first have done all those operations, and then from the last row, we subtracted the original first row. But this operation, again, it is, well, not very much legal, so it changed the determinant. But how it changed, that's the question.
Maybe we should write this an minus a first one, then write an minus, just to write these operations, what happens to the letters while we subtract them, and then compare it to our formula of the determinant.
Oh, no. I understand what you're talking about, but you will obtain a huge formula and it will be very hard to understand anything inside.
Maybe it changed because we changed the element of diagonal. That's why it changed. So elements have to be we don't have to change the elements of the diagonal.
I'm sorry, but how is it connected to my question? I mean,
Can you repeat the question? Maybe
yes,
I
again, someone, okay, so we discussed, someone did the following operation with the determinant, okay? I don't know, I don't know, Alice had a determinant A and Bob has written a determinant B. We've discussed that there is a naive idea that maybe determinants are equal because something. And we've discussed that this proof is wrong. There is no reason, at least our reasoning doesn't work. Determinant of B is not equal to the determinant of A because of properties of elementary operations. Then the question arises, what does the determinant of B equal to? How to find the determinant of B?
Maybe this idea will be stupid way, but maybe +2 just to the main determinant.
Again, what do you mean? I can't understand.
I mean that I've seen that the разница как будет?
Difference?
The difference between the in our examples, the difference between B and A are just 2. So maybe this is the
That's
case.
because this is an example, you know, in some particular examples, there are some particular numbers, but in the general situations, well, why 2?
No, I think that it's gonna be the one number which depends on some logic.
Okay,
So,
but if you take, if there are, for example, 3 rows in A, then after you apply this procedure, you will obtain the following 3 rows. I'm sorry, not correct. Okay, now they are not the same as here. It is just because this example was 2 by 2, it was very small. When it becomes bigger, it is slightly more complicated. Yeah, in the first example, simply in one row we had A1 minus A2, in another row we had A2 minus A1. But in the more complicated situation, they are not all equal.
Well, I just was thinking about to write the general idea of what's happening to the rows while we're subtracting them,
Mhm.
like an minus a1 minus an minus 2 plus an minus 1, for example. And then compare to the a1 minus a2 minus an minus a1. And then we subtract the last, from the last row, we subtract the first one, we just see that some elements are gone, like a1, and we got the minus.
Okay, and so what?
Well, the others
How
ones
does it
still
help
get,
us to find this determinant? Again, we have already discussed why it is not equal to the original one, but what is it equal to? How to find it? So, okay, we've tried for like 5 minutes. So let me produce an idea. We can take this expression and start simplifying it the same way as we did, well, like several previous problems. We can perform now some operations with this b to make it simpler, to cancel some of those elements. And maybe at some point, we will be able to find the result. So again, there was some Alice with determinant A, Bob with determinant B. Now we take his work and start computing it. The question is, what is the determinant of B? Answer, let's find out. So I suggest that we take this and start simplifying it, start doing some operations on those rows. For example, I may add the first row to the second row. If I do this, then the second row becomes A1 minus A3, right? A2 cancels. Now, what would you suggest to continue this idea?
well,
The good news are that A2 canceled here.
But why we have a3, maybe a2 minus a3.
No, it was A2 minus A3 before I added. Now, after I add A1 minus A2 to A2 minus A3, A2 cancels and A1 minus A3 remains.
And we just added like that several times in the first row to each other next one, yes?
We could add the first row to each next one, but it doesn't seem like the good idea.
Yes,
because
but
if we
what
add this
about
to here,
add the second one to the third one, and then we will get.
yes, very good. We can add the second row to the third one so that 3 also cancels. Let's try. What we obtain looks as follows. Here we have first minus second. Here we have first minus third. Here I obtain first minus fourth. And the next one is yet unchanged. So obviously now I repeat this procedure many times. And what happens in the end? So the first rows look as follows: A1 minus something, A1 minus something, A1 minus something.
The first column becomes consists of the one element, just only the last one is different.
No. Why do you think so?
It's because we have A1,
row. A1 is a row of the matrix A, and A2 is a row. When you subtract rows, well, every element might change.
Okay.
So what we obtain is as follows. If I don't change the last one yet, then they become A1 minus A2, A1 minus A3, etc., A1 minus AN. And now I may finally add this to this. What I obtain is now the following. When I add this row to this row, everything cancels, and I obtain the 0 row. So that is the row full of zeros. But this means the determinant equals 0. Because in every sum element of the sum from the definition, there is some element in this row, and it equals 0. Okay, it didn't work as well as I hoped. But still, if you have any particular questions to this solution, please ask. Maybe I will clarify something.
I guess it's more or less clear that yes, the first one columns are we have not 0 results for each row, I mean numbers, but while if we subtract the first one from the last one, then we got the 0. And
well,
then,
we're not really subtracted the first from the last, because the first again was A2 minus A2, A1 minus A2, and the last was AN minus A1. But we subtracted them like many times.
Yes.
So, and at some point we obtained 0.
And then we just to the row which is equal to the 0, we try to add the first row, and then we get that A1 minus A2 in the last row. Not add, but subtract. And then we get yes A2 minus A1.
Why A2 minus A1? It is
But in the task we just have that we have this abstract rows from each other on the first one.
I don't understand you, sorry. Yeah, so
Okay.
Okay, I don't know how to retell what I did in yet in other words, but I simply performed something similar to elimination by simplifying each row until I found 2 equivalent rows, and they canceled each other. Oh, why this 0 somehow moved? I see, because I moved the frame. Okay, I'm sorry. It looks like not everything was very much clear in the last problem.
So I just see that we try to understand what the determinant will be. We subtracted the first row from the. We just subtracted from the next rows the previous ones.
Yes, we added the previous row.
Added.
Yes.
Yes, added even. And then we just got the 0 in the last row. And
yes.
if we have in the last row 0, then the determinant.
Yes, then the determinant itself is 0.
Is
Yes,
0.
that's what happened. And there is a more interesting problem of the same type, which we don't have time to solve, but let me simply at least write it here. So in case someone is interested, I recommend to consider it because it is slightly more hard and more interesting. You can use the same approach, but there is a big, it is not so easy. I'm sorry to finish at such a sad note. Again, I feel some uneasiness in the air, but still time is up. So let us meet at Saturday and we will discuss more interesting determinants and some more tricks and Cramer's rule, etc.
Thank you for the lecture.
Okay,
Okay,
Thank you.
thank you for
it's
the.
not a lecture.
Bye.
I hope.
Yeah.
Good luck.
Yeah, thank you very much. Goodbye.
Goodbye.